Good morning, afternoon, evening, dual enrollment college algebra folks. This is Solving Exponential and Logarithmic Equations, section 4.4 in our unit 4, which is exponential and logarithmic functions. Okay, so there's basically several different strategies to solve equations, and what you have in front of you when you're trying to solve logarithmic or exponential equations, what you have in front of you helps you decide which strategy you have to use. And that can be the most complicated thing about this. So let's look at our first strategy is, first of all, they're exponential equations. Okay? Notice you don't see the word log anywhere. It's all exponential stuff. By expressing each side as a power of the same base. Okay? And they point out if something to the m power equals that same thing to the n power, then m must equal n. Well, that kind of makes sense. Okay? It's just the same as if I said if 5 to the x equals 5 to the second, then I guess x is yes. Sorry, couldn't see that. That's the general idea we're using. So when I look at an exponential equation, my first question is to myself is, can I write those two bases for the two main numbers on each side? This isn't really a base, but we could think of that as 8 to the first power. Can I write those two bases as powers of the same number? Like as 3 to a power, 4 to a power, etc. In this case, 32 and 8 can both be written as a power of 2. This is 2 to the 5th. That's what 32 is. And there's still that x. And 8 is 2 to the 3rd. Remember from algebra that when you have an exponent inside parentheses and one outside like that, we can multiply these. Or we should multiply these. So this means 2 to the 5x equals 2 to the 3. So if 2 to some power equals 2 to something else, these two powers must be equal. 5x must be equal to 3. So 5x equals 3. X is 3/5. Next, I'm asking myself if 8 and 16 can both be written as powers of the same number. The answer is yes, they're both 2 to a power. Or 2 to the 3rd here. And 2 to the 4th here. Now, just like over here, we're going to multiply. It's a little bit more complicated here, though. It's 3 times all of that, so don't forget to put it in parentheses. You're distributing the 3. In other words, this is 2 to the 3 times x plus 3, and 2 to the 4 times x minus 1. 4 times the quantity x minus 1 is how we could say that, or 3 times the quantity x plus 3. And now I'm going to distribute. Actually, I don't have to do it now. I can see that they're both exponent 2 as the same base, so I can go ahead and just say that means this must equal this. So 3x plus 9 must equal 4x minus 4. That gives me x equals 13. Finally, don't forget that when something is in the denominator, you can move it to the numerator by giving it a negative exponent. In other words, this is e to the first. That's the same as e to the negative 1. That whole expression is the same. This whole thing is e to the negative 1. All right, so that means x plus 1 must equal negative 1. So subtract 1. I got ahead of myself there. And I get negative 2 for x. This is subtracting 1 from both sides. So that was my strategy when I have an exponential equation, is ask myself, can I write these two numbers, the bases, as powers of the same root? 2 to some power, 3 to some power, 4 to some power usually. Or in this case, e to some power. And when you can, it's actually one of the simplest ways to solve an exponential equation. Next up, using natural logarithms to solve exponential equations. Okay, they have an exponential equation, and what they're saying is either, well, here's what I'm looking for. We're going to take the natural log of both sides, and then we're going to use properties of natural logs. Okay, in other words, I'm going to go ahead and add, remember you can do anything you want to both sides as long as you are equitable about it, and that still applies to taking logs. Now they chose, well, let's finish this problem before I say that. Natural log of both sides here. Okay, the x, remember we can move that out in front of a logarithmic equation, or a logarithmic expression rather. So that means this. So if I want to get x alone, which is what solving is all about, that'll do it. X equals the natural log of 143 over the natural log of 19. Here's why we're using natural logs, is because natural logs can be put in the calculator. So natural log of 143, don't forget to close your parentheses, divided by natural log of 19. And I get 1.685. Let's go to the hundredths place, so that would be 1.69. So x is approximately 1.69. Now, this is what I said I was going to come back to. It doesn't have to be natural log. Theoretically, you could take the log base 5 of both sides or the log base 11 of both sides. You could take whatever log that you want to of both sides. The reason we use natural log is because it's in the calculator. So is common log. So you could have just as easily taken the common log of both sides, log, and you would end up with this. Okay? And then when you go to your calculator, you would get the same thing. So we're basically just taking the log of both sides, and we're doing it in a way that's convenient by picking one that's in the calculator. All right, so let's do that again over here. And natural log, I don't know. I think a lot of people just like writing it because it's sort of nice and cursive and flowy and quick. So let's use the natural log. Here's an exponent. And this is what it does. It allows me to pull that out. That's the whole joy of this. This is why we do it. And now it's not up in the exponent. It's right there with all of our other numbers where we like to deal with things and work with them. Okay, so x plus 2 equals this. So let me go ahead and put that in the calculator and see what natural log of 410 divided by natural log of 7 actually is. 3.091, let's go ahead and just 3.09. Is x alone? No. Solving for x means getting x alone. So we need to go ahead and subtract 2, and then we get 1.09. All right, last but not least. First, before we do any of this, we really want to have an exponential situation on one side, just b to the x, something to a power. Okay, here we're not there yet, so we're going to go ahead and simplify. We're going to put it in that form is really what it is. We're going to make it so that one side of my equation is just something to a power. So this is 11,250. Now, sometimes it's kind of intimidating to folks to see the e, but especially if we're going to use natural log, the e is really more convenient. Okay, because remember, and let me write this first before I show you. Excuse me. Let me see if I can find my properties that I wrote down for you in the last video. Here we go. Remember this property right here. Right there. Okay. This means that log base e of e to whatever power is just going to be whatever power. Which means natural log of e to some power is just going to be that power. That's what this means. Log base e is natural log of e. So, this whole side of the equation just becomes 4x minus 5. Not log of 4x minus 5, just plain 4x minus 5. And I'm going to add 5 to both sides, and I'm going to divide by 4. And I'm running out of room, so let me grab another piece of paper. That's right, 4x equals natural log of 11,250 plus 5. So x equals natural log of 11,250 plus 5 all over 4. This is not in here. It's not natural log of all of this. It's natural log of just this, and then when I'm done with that, adding 5. I like to do what I just did, which is get x alone before I put anything in the calculator. Go ahead and solve, go ahead and isolate x, and then type in what the opposite side says in the calculator because that's your answer. So natural log of 11,250, close those parentheses or else the plus 5 would be included. Plus 5, and I'm going to press enter and then divide by 4. I like to kind of walk my calculator through the order of operations just to make sure it's doing it right. This is a decimal approximation. Anytime you round from your calculator, it's a decimal approximation. And theoretically, we should write the little squiggly equal sign to say x is approximately equal to 3.58. Most people won't necessarily count. Well, I'm not going to count off right now if you don't, but you should. Let's put it that way. All right, so that was strategy number 2. Notice it was a strategy, again, for exponential equations. So you didn't see any logs in the original equations. Okay? Notice also that the first strategy wouldn't work on these. So this is a really good go-to when the first strategy doesn't work. If I ask myself, is there a way to write 19 and 143 as powers of the same root, or same base, rather? No, there's not. 19 is not anything to a power if we're looking for integers, which we are. Okay, so we couldn't use the first strategy here. Next, we are transitioning over to logarithmic equations. And basically what we're using to do it is rewriting. When we talked about rewriting, I told you it was one of the main ways we could solve equations, and that's exactly what we're going to do. Let me remind you of how I perceive rewriting. And your teacher may have done it differently, but your teacher in Algebra 2 or Pre-Calc, I like to think of it this way. When I look at a logarithmic equation, I see log base answer equals exponent. Answer is not the best word for it, but this is just what we're calling it. What this means is when I transition this to an exponential, I have my base to my exponent and then equals, and the opposite side, that's what we're calling the answer, is the opposite side, the thing that's on the opposite side by itself. Some teachers teach it as you do it like this. B to the C equals X. Same idea. And that's what you see actually right there. My concern is I feel like people can get confused by which way does the circle go, which way do I, etc. But if you don't, that's great. So this is log base answer equals exponent. So my base is 4, my exponent is 3. 4 to the third equals, and then 3x plus 2 is the answer, so to speak. And by answer, again, I mean the thing that's by itself on one side. So this is 64 equals 3x plus 2. Subtract 2 from both sides. Divide by 3. And you have 20 and 2/3. Or we could just leave it at 62/3. You could say 20 and 2/3 or 62/3 is absolutely fine. There's nothing wrong with a quote, quote, improper fraction. All right, now look at this one. In order to do this, in order to do any of it, whichever way you see it, notice you start out with a sort of simplified logarithmic expression. In other words, it needs to start out log some base, some argument equals something. It needs to start out looking like that. If you have multiple logs on one side or something else, you either need to figure out, can I simplify this so that it's just one log on one side? And the answer here is yes. It's addition, so that would be multiplication. I can put those together. I can condense that expression by multiplying x plus 3 and x plus 4. And now I need to go ahead and multiply that out. I could wait, but I could also do it. There's really no preference in terms of when we do it. Excuse me. Well, yeah. So this is x squared plus 7x plus 12. I used FOIL or distributive property to multiply those. And now I'm going to rewrite 6 to the first power equals this. Log base answer equals exponent. So 6 to the first equals x squared plus 7x plus 12. Now, how do we solve quadratics? Well, we start by getting them in standard form, which means everything's on one side and zeros on the other. So I'm going to go ahead and get this in standard form, and it looks like this. Then my favorite way is if it's factorable, factor it. If it's not factorable, quadratic formula. This is factorable. Two numbers that multiply to give me 6 and add to give me 7 are 6 and 1. So that's how I can factor that. So x equals -6 or x equals -1. Okay, so now let me point out to you, when we talked about, oh gosh, let's see, I have it on my desktops here somewhere. If I can find the graph, I will show you. When we talked about, voila, I think I did, the graphs of logarithmic functions. The domain is not all real numbers, meaning not all x's will work. So we really always, I should have done it over here too, we really always have to, and it says it right here as a matter of fact, check the solution and see if it actually works. Okay, this one would be easier to check if I leave it in this form. I'm going to say log base 4 of 3 times 62 over 3, which basically means it'll just cancel and be 62, equals 3. Well, 62 plus 2 is 64. So this is saying that log base 4 of 64 equals 3. Does 4 to the third power equal 64? It does. So yeah, that works. Here we want to go ahead and plug these back in. I would probably plug them back in right here, because we'd need to put it together if we put it in here. So -6 plus 3 is -3. -6 plus 4 is -2. -3 times -2 is 6. So that would be saying that log base 6 of 6 is 1. Is that true? It is. Okay. Now let's try. That was me checking -6. Let's check -1. -1 plus 3 is 2. -1 plus 4 is 3. 2 times 3 is 6. Get the same thing. So yes, they both work. Always check your answer when you're solving a logarithmic equation, simply because all the x values in one part of the graph are not going to work. It's not always necessarily just negative x values, because remember, we've got horizontal shifts going on here, so that asymptote can move. Okay, you just have to check your answer is what it is. All right, last one on this page, we have subtraction. So that's going to be a quotient rule applied. Equals 1. And now I'm going to rewrite 4 to the first power, that's 4, equals x plus 2 over x minus 1. Okay. So now I'm going to go ahead and multiply both sides. I'm actually a little trepidatious here. I'm thinking about this. I know that x cannot equal 1. So we're going to have to go ahead and stipulate that. X can't equal 1 because we can't have a 0 in the denominator. So assuming x is not equal to 1, we're going to multiply both sides by x minus 1, excuse me. We just can't forget that x is not allowed to equal 1. So this gives me 3x equals 6 and x equals 2. So x can't equal 1. We're good. It doesn't, so we're fine with that. And I still need to check this answer. I'm going to check it right here. 2 plus 2 is 4. 2 minus 1 is 1. 4 over 1. So log base 4 of 4 equals 1. Sure does. And so we're ready to stop there. All right. Our next objective is also solving logarithmic equations. So we've learned so far, we've had 2 strategies for solving exponentials, and this is going to be our second strategy for solving logarithms. And I'm going to pause right here, so pardon me if later I'm redundant. I'm going to pick up here in making the video, but the bell's about to ring. So come back to you in a sec.